Mo the mole wants to vandalise this garden. Think of the garden as being made up of n-squared cells, so the garden has side of length n and width of length n as well. And we're told that the mole begins by vandalising the middle cell. The rules for Mo's behaviour is that henceforth they can damage a new cell, provided that new cell is adjacent to a cell which has already been cleared and is in a run of 3 consecutive uncleared cells. So at this point, the mole can vandalise the cells immediately left, right, up or down of the existing cleared cell. And the issue is, Mo the mole can do this for a while, but eventually the rules will prohibit the mole from doing any more damage. What is the least number of squares that can be cleared before the mole gets stuck? Well, you have to imagine squares get cleared for a while. How could he get stuck? Well, in fact, what happens is that the mole cannot get stuck unless the mole has reached all 4 sides of the garden. That's not completely obvious, so we have to prove it. So, for example, let's show that the mole must reach the top before it gets stuck. So suppose that it gets stuck with a top row which is not at the edge of the garden. So somehow gets stuck before, perhaps somewhere in this row. Well, if there is any square in this row, not the n squares, but any row, any little square in this row which is cleared, then the mole can build up. But if this is the top row which contains a cleared square, then in fact the first square cleared in this row must not be an n square, because think about how an n square could be cleared. It can't be cleared when all of the squares in this row are uncleared. It can't be cleared from below because it doesn't sit in a row of 3 consecutive uncleared squares. So the first time there's a cleared square in this row must be in the middle, not an end square. But of course, if there is such a cleared square, not at the end in this row, then mole can build above. But we're supposing that Mo the mole is stuck. So the only thing that can happen is if the top row in which there is a cleared square and mole is stuck is the situation when the top row is the edge of the garden. Now that argument works in all directions. So for the mole to get stuck, they must have cleared regions which, well, they must have cleared a square along each of the 4 edges. Now the region that they clear must be connected. You can get from any square which is cleared to any other square which is cleared by, as it were, walking along a path through cleared squares. So there has to be a path from the left, one of these leftmost cleared squares to one of the rightmost cleared squares. And also there has to be a path from one of the topmost cleared squares to one of the bottommost cleared squares. Now, how do you make these paths? Well, it's left-right moves, horizontal moves, which enable you to go from the left-hand side to the right-hand side. And the up-down moves, vertical moves, are what enable you to go from the bottom to the top. Now, there's one cleared square at the beginning. In order to get a path from the left-hand side to the right-hand side, you have to clear at least n minus 1 squares using horizontal moves. Similarly, you have to clear at least n minus 1 squares using vertical moves. So altogether, you must clear at least 2 times n minus 1 plus 1 squares before you get stuck. So now we're going to see that this bound of 2n minus 1 can be achieved. Of course, you can't really draw an n by n diagram, so I draw a 7 by 7 diagram. The argument generalizes, there's nothing special about 7, other than the fact that it's odd, but it has to be odd in order for there to be a central square for the mole to begin. So mole first damages this, and then what they do is they go left down alternately. So mole clears this, which they can do because those 3 were clear. Now these 3 are clear, so mole can clear this. These 3 are clear, so mole can clear that. These 3 are clear, so mole can clear that. And then these 3 are clear, so mole can clear this. Mole hasn't yet reached the bottom, but there are 3 uncleared squares here, and this is cleared. So mole can clear that. And mole has now reached the left-hand side and the bottom. Now let's go up here. So we were going, let's see, let's go up, then right. So this becomes an 8, this is a 9, this is a 10, this is an 11, that's a 12, and finally we've reached all of the sides except the rightmost side, but these 3 are uncleared and that's cleared, so we can put 13 in there. And now, if you stare at the diagram, you will see we are stuck. There is no cleared square which is edge adjacent to a run of 3 consecutive uncleared squares, and you can't continue. So essentially you've got this sort of wonky diagonal running across the board, and that gets you stuck. And 13 is 2 times 7 minus 1. So we have achieved the bound. And try any odd number, all that happens is this diagonal gets a little bit longer, but otherwise everything stays the same. So that's a proof.